Welcome to this video on geometry angle vocabulary, including basic definitions and basic intro problems. You'll start out with some vocabulary and labeling. For the definition of congruent, we will basically say that these are going to be equal in measure, and this may apply to segments, angles, shapes of various different kinds, and we'll apply that a lot over the next few slides. So as you can see in the pictures below, an angle can be named by a point. It can be named by an angle, like in the middle at the bottom here, as an angle 1, or 3 points with the vertex in the middle. And this third part of this sentence is crucial because we'll see a lot of angle QRS in what we are doing in this chapter, and you'll have to know that you're kind of going and keeping that middle letter R as the main part of the angle at the vertex, which we can mark. And we can keep moving now through our slides. Before we talk about what this specific is, postulate is something in geometry that is a known quantity, and it is not something you have to prove. It's kind of accepted as being true. Specifically, this angle addition postulate is, as you can see at the bottom, we have a larger angle, which is angle ABD in front of us. And we have two smaller angles, ABC and CBD. If each of those parts are 16 degrees and 11 degrees, that would mean that the whole angle ABD, would be 27 degrees. And that remains true no matter how many times you split up a larger angle into their individual parts. In example 1, we're going to apply the angle addition postulate. And the way we're going to do that is the fact that if this QRS large angle is equal to 62 degrees, we know by that postulate that this expression x plus 3 plus 5x minus 7 is going to get us the angle measurement at the bottom, which means for us that we can do 62 degrees would be equal to x plus 3 plus 5x minus 7. And we're going to just combine like terms on the right side to get 6x minus 4 is equal to 62. And then we can add the 4 to both sides so that we have 66 is equal to 6x. And if we divide both of those sides by 6, we would get an answer of 11 being equal to x. And we have added these two smaller angles together to get our larger angle in order to make that happen. Our next definition is an angle bisector, and it is defined as when something is cut in an angle and exactly in half, or in two, however you wanted to put that. And angles are going to be either congruent or equal. And we'll write both down here. Angles are congruent. Just remember that that means the same or equal. And frequently you'll see angle markings like a little kind of stripe there, 2 of them. And then on this angle, MKL, we do have another 2 of these to show that they both have 2 angle markings and that segment KM is bisecting that angle. Now I have an example number 2 where we're going to be using the angle bisector theorem. And angle bisector theorem is known as a theorem because we had to understand different things like the angle addition postulate, for instance, in order to figure out that the angle bisector is a thing that we can use. So let's use it in this problem. We know that because KM is bisecting the larger angle JKL, that means that this angle and this angle are both going to be equal to each other. So we'll put like one angle marker in both those places, and we can set these two equal to each other. So I can say that 3x minus 7 is going to be equal to 2x plus 10. And then I'm going to be using some solving equation skills to finish this one out as well, like last time. So I can first add 7 to both sides. And I get that 3x is equal to 2x plus 17. And then I just subtract 2x from both sides. So I have 1x, or just x, is equal to 17. And so that, in this particular problem, is our final answer. Keep an eye out for problems in the future where it not only just asks for x, but also might ask you to put that x back into the original picture and figure out what the angle would actually measure once x is substituted in. Our next definition that we're going to talk about, the adjacent angles, are basically angles that share a side and a vertex. And so we can put in a vertex for our first blank here. And what we can say are not, and what I'm going to fill this in with, is necessarily equal to each other, or not necessarily equal, because they could be equal. We don't necessarily know just based on the information in this picture, but we can we know that they're basically just next to each other. That is what adjacent means, something being next to something else. So not necessarily equal. So let's go ahead and continue on here. Which angles are adjacent or next to angle CFD? So we're just going to mark all the ones that are next to it. So this angle right here is the angle they're talking about, CFD. So we would say that angle DFE is adjacent to it, CFB is adjacent to it, but the only one up here that is not adjacent to it would be this one over here, angle AFB. The other three might not be equal to the angle we're talking about, but we have two angles that are in fact next to the one we care about here. Let's continue forwards with our notes. Now we have vertical angles. So angles whose side form two pairs of adjacent angles and another thing we could say about this first blank is we could also say two pairs of intersecting lines. So we could say intersecting lines, intersecting lines. And vertical angles are congruent. If we look below in our picture, we can see four different angles, and we have two pairs of congruent angles. The ones across from each other are congruent, so 4 and then 2 are congruent. And then also 1 and 3 are congruent to each other as well. And we'll now look at an example here where we're applying that knowledge. We know by vertical angles that these two angles are congruent or equal to each other. And so I can write 3x minus 63 is equal to x plus 37. And I can just use my solving equations to subtract 2x from both sides first. Subtract x from both sides first. And we would need to get rid of the numbers second. So I would have 37 over here on the right. So if I am adding 63 to 37, that equals 100. 2x would then equal 100. And that means that our value for x is going to be 50. Let's keep moving to more of our notes. We now have complementary angles. Complementary angles add up to 90 degrees. And keep in mind that complementary is spelled different and is a very different word than a compliment you might pay somebody if you're saying something nice to them. This is a different word entirely in the math kind of geometry world. And the angles add to 90 degrees, and these angles will also form a right angle, given that right angles are 90 degrees. And you can see below that JKM and MKL are complementary angles, and they would in fact add to 90 degrees. We have an example here of a complementary angles problem. And we have a 90-degree symbol here. And that means that this whole angle over here is 90 degrees. So 12x minus 13 added to 4x minus 9 would have to end up being equal to 90 degrees, these two added together. So I'm going to do that up here at the top. 12x minus 13 plus 4x minus 9 is going to be equal to 90 degrees. So let's combine like terms. 12x and 4x is 16x. And negative 13 and minus 9 would be equal to 22, negative 22. And that is still equal to 90 degrees. Now we can add 22 to both sides, and we get 16x is being set equal to 112, meaning that if we divided both sides by 16, we would get an answer of 7 being equal to x. That's an example of a complementary angles problem. Now, supplementary angles is our next vocabulary word. So we know angles add here to 180 degrees, and they form a straight line. A line would have an angle of 180 degrees, so you have two angles down the bottom. We'd add them together to make 180 degrees, and without the angle lines making kind of YZ and BA, you would just have a straight line right across from X to C. For number 6, we are looking at two supplementary angles, so we need to add these two together. So if I added 5x and 4x, I would get 9x. And if I added 23 and 22, that would give me 45. So I have negative 45. I've combined those two angles together now, and I've set that equal to 180 degrees. Add 45 to both sides, and now we have 9x is equal to 225. 225 divided by 9 is equal to 25 for our x value. In example number 1 in front of us and the next 3 examples, we're going to be using various vocabulary words we've just finished going over in order to solve for x and identify missing angles in front of us. In number 1, to start with, we know WOZ right away because we can see there's a 90-degree angle written in there. So we can just fill that in right away as one thing we can check off. Something I want to point out about this problem is you can see that the 90-degree angle marker is in the middle of this angle. But whenever you see a line cutting through it, you don't want to assume how big or small these two smaller angles are going to be. So we need to make sure we're using math to support everything that we're doing. And so let's label our triangle, our angle, with some of the variables and expressions we have over here. So YOZ is the one that is 10x. And 19x minus 26 is our other part of our angle as well. And so now we know that they are complementary and have to add up to 90 degrees. So we have 19x minus 26 plus 10x is going to be equal to 90. And we can combine the 10x and 19x to get 29x. And add 26 to both sides. So we have 116. If we divide both sides by 29, we get that x is equal to 4. Not 4, not 40. And we know we can fill that in for x down at the bottom. And YOZ is 10x. So 10 times 4 would mean this is a 40-degree angle. And just by process of elimination, 90 minus 40 would only leave 50 degrees left for angle WOY. And that completes problem number 1. Problem number 2, we have a line RAN and then a line ray going AM. So we can tell that these two angles are on this line, and that means they are supplementary angles. So we can add these two angles together and have them, that would equal 58x, and negative 10 plus 16 is 6. And that has to add up to 180. And we can subtract 6 from both of those. So we have 58x being equal to 174. And that means that x, when we divide by both sides by 58, is going to be equal to 3. Fill in 3 for x. We know RAN is just a straight line. It is 180 degrees. We can use our x equals 3 in angle MAN, because 8 times 3 is 24. 24 plus 16 is equal to 40 degrees. So 180 minus the 40 we've already found will give us 140 degrees remaining, and we could put in x equals 3 into this one. 50 times 3 minus 10 does equal 140 degrees, so our answer was correct. And that completes problem number 2. Problem number 3, we have angle CAN over here, and then we have an angle MAT over here. So those are vertical angles, and we know they're equal to each other. So we know that these two expressions they have given us are equal to each other. So that we want to write it out as an equation first in order to solve it from there. And you're going to look for x from this. And we can subtract 15x from both sides and then add 1 to both sides. So we have 3x is equal to 21. And x is going to be equal to 24. Or no, equal to 7, actually. When we divided by 3, x is going to equal to 7. So the first thing we can do is put in x equals 7 over here. And we know that for CAN and MAT, we're going to have to use the x being equal to 7 to solve those equations. So we can do 18 times 7 minus 1 will be equal to 125 degrees. if that's 125 degrees, we know angle MAT is 125 degrees as well. And we can write that in. And if we're looking for the angles, the two angles we are missing, we're missing 3. Angle MAN is just a straight line. So that's like before, 180 degrees. The two angles we now have missing, MAC and TAN, are both equal to each other. All we have to do to get the answer is 180 degrees, or 180 degrees, which is MAN, minus MAT or CAN. That difference is 55 degrees. So that difference would be the angle they're missing here and here. So we know that these two were both 125, and then both of these angles were both 55. And that completes problem number 3. Problem number 4 will be our last one in the video, and there's a lot going on in this problem. We want to think about what we could label down here to start with. Angle QPR, which is right here, QPR, is going to be 90 degrees. We know that it's marked by that box showing that it's 90 degrees. If we look at the other ones we have here, it doesn't seem like we know any of those other parts. So we could say up here, TPQ is not one we need, but we do know it's 90 degrees. So that's going to be helpful later on. So we need to use these two expressions to add them together in order to have them equal to 90 degrees, since they add together to equal angle QPR. And so we can do 7x plus 5x is 12x. Negative 12 plus 6 is negative 6. And that is equal to 90 degrees. And if we add 6 to both sides, we've got 12x is going to be equal to 96. And 96 divided by 12 is going to be equal to 8. So we've got our x value. Now, in order that we can figure out what QPS and SPR will be, so let's do that first. We can do QPS first. So we're going to do 7 times 8 minus 12, and that is going to be equal to 44. And so we got QPS. So SPR, using this expression, we would do 5 times 8 plus 6, and that is going to be equal to 46. And we want to label our picture here. So we know SPR is 46 degrees and QPS is 44 degrees. So that adds up to 90 degrees. That's a good sign that we did it correctly. And we're missing 2 angles. So we're still missing SPT. If we go and label this angle right here as 90 degrees, we can say SPT would just be 90 plus 44, and that would equal to 136 degrees. So TPR we missed earlier, that was just 180 degrees. And we have now found everything we needed in this problem for number 4. And that concludes our presentation lesson on geometry basics, vocabulary, and examples for angles. Thank you for watching.